Hello everybody and welcome to chapter 2 of Calculus and Vectors. Today we will continue looking at derivatives, but now more in depth. So all of chapter 2 is essentially work with derivatives. We're going to learn about different rules that apply, as well as how we can use derivatives to help us solve real world problems. So chapter 2.1 focuses on the derivative of a polynomial function. More precisely, today we're going to cover some derivative rules, not all of them, but most of them, as well as we're going to cover 3 types of problems that we can solve now using these derivative rules. So let's take a look at that. To quickly solve derivatives of functions, we need to have some kind of rules to follow, because as we've seen in chapter 1.5, even something really basic like x to the power 3 takes a really long time to solve because you have to apply everything to the first principle definition of derivatives, which takes forever because you need to find f of x plus h and then f of x, and then you need to make sure that everything cancels out properly. But luckily for us, mathematicians years ago have figured out some rules that we could follow that make that whole process a lot easier. So the first rule is the constant rule, which says that if f of x is equals to c, where c is any constant, then the derivative of x would be equal to 0. So here I actually have both the notations that you need to know. Again, I'm not gonna try and pronounce the names of the mathematicians that created these notations, but as you can see here, we have the f of x one that we're familiar here, and the d over dx. Notice that we don't have dy over dx, and that's because we needed to actually say what we're working with. But yeah, that's the difference in notation. So following the constant rule, we actually have the power rule, which says that if f of x is equals to x to the power of anything, as long as it's a positive integer, then f prime of x is equals to n times x to the power of n minus 1. So if it was x squared, our derivative would then be 2 times x, and then 2 minus 1 is 1, so 2x would be our derivative. If it was x to the power of 3, our answer would be 3x squared. So you could do that now super quickly without having to go and do the first principle notation or a derivative. The next rule that we need to know is the constant multiple rule. This one is pretty simple. It just says that if you have a function, which is actually a constant times a function, then the derivative of this would be equal to the derivative of the function times the constant. So if we had 2x squared, then we would have 2 times the derivative of x squared, which was 2x, and so we have 2 times 2x, which is 4x. Again, these are the different notations. One important thing I want you to notice is that I've written like a space here. Remember, this part should be a fraction, so this should be a fraction of this over here. So it's not necessarily times, as you see over here, but it's just the best way I could possibly write it on slides for you to understand. The next 2 rules that we need to know are very similar. The first one is the sum rule, which states that if the functions f of x and g of x are differentiable, so you could find the derivative of them, then and h of x is equals to the sum of these 2 functions, then the derivative of h of x is actually equals to the derivative of the first function and the derivative of the second function. So again, just to illustrate, it's saying if you had the function x squared plus 2, you'd find the derivative of x squared, which is 2x, and then you'd find the derivative of 2, which is 0, as you can see here. You add those 2 together and you'd find the derivative of h of x. Similarly, the difference rule just states that if you subtract one function from another, then the derivative would actually be the difference between the derivatives of those functions. So if you had, again, like x squared minus 2 this time, you would have 2x minus 0. So again, you're just going to substitute those in, solve each one individually, and then find the difference at the very end. If you want to prove the validity of these rules by yourself, you could use the first principle definition of the derivative to actually figure all of these ones out. So if you want to do that as like a bonus challenge, you could go for it. All you gotta do is just substitute these equations into the first principle definition. Notice that the power rule will require you to factor, and it will be like a sum of almost an infinite amount of numbers. So you'll need to be on the lookout for that. But if you're interested, the full derivation of that is actually in your textbook on page 77. So check that out if you want. So learning about these rules isn't really beneficial if you don't learn how to apply them. So here I've got us 2 examples that we can work on to practice these skills. So let's do those quickly. So okay, let's now look at question number 1. We're given that f of x is equals to x to the power of 8 minus 4x to the power of 6 plus 2x to the power of 3, all divided by 4x cubed. So immediately what we should do is cancel out any like terms. We know that everything here has at least an x to the power of 3 within it, so let's remove that. If we cancel out x to the power of 3 from x to the power of 8, we are left with x to the power of 5. Similarly here we would have x to the power of 3, and over here we just have a 2. And now at the bottom we'll be left with a 4. Now what we could do is either express this whole thing as separate terms, or you can try to differentiate it this way. I'd prefer if we split up into different terms so we could learn how to apply each of the derivative rules more effectively. And so in doing that we would get x to the power of 5 divided by 4, nothing cancels out there. Here the 4's would cancel out and we'd just be left with x to the power of 3. And over here would be left with 1 over 2. Now what we can actually try doing is differentiating it. So what rules do we know of thus far? Well, we know that here we have some power, so we could use the power rule. We also have some constant, the constant here, and we also have something multiplied by constant. So if we want to, we could actually split it up into all the parts that we know we're dealing with. So let's do that. There you go. From here, let's actually apply our derivative rules. The first one we can do is the constant times the derivative of the function here. So our constant would be 1 over 4 times the derivative of x to the power of 5. Well, what's the derivative of x to the power of 5? Well, using the power rule, we know that it should be of the format n, x, and minus 1. So here, our answer would be 5x to the power of 4 then. Similarly here, we would then get 3x squared, and the derivative of a constant is actually 0. So now, if we open these brackets and continue, we would actually get 5 over 4, x to the power of 4, minus 3x squared. So this right here is our final answer. We could factor it if you wanted to find the roots, for example, but it is not necessary in this case since we were asked to just find the derivative. So now let's actually look at question 2. So 2, we have y is equals to x to the power of 5 over 15 minus 2 square root of x. So this one here requires different notation, right? Since we're given y. So what we can do, we can first of all try and figure out what parts we have here. So y is equals to x to the power of 5 over 15, that stays. That's also the same as x to the power of 5 times 1 over 15, but we could do that in the next step. But here we actually need to recognize that x, like the square root of x, is the same as x to the power of 1 over 2. And in doing this, we can actually apply the power rule later on. So now actually let's write out all of the parts that we can see. So here is the constant multiplied by our function, minus 2, again a constant multiplied by a function. Using the notation that we've learned, we can actually find the derivative of this function either by saying y prime or by actually using the notation of du over dx of y, which would be dy over dx, is equals to 1 over 15, the derivative of x to the power 5 minus 2 times the derivative of x to the power of 1/2, right? So this is what we get. You can put brackets around it if you want to visualize it better. So this right here would give us the following. Again, using the power law, we know that x to the power of 5 is the same as the derivative, or sorry, is the derivative that equals to 5 x to the power 4. So 5x to the power 4 minus 2. And the derivative of this one might seem a little bit more tricky, but it's not, because remember, again, the formula is nx n minus 1. So our n value is 1/2. Our x value stays the same, and then n minus 1, so 1/2 minus 1 is negative 1/2. So from here, what we can actually do is simplify this portion right here. We can also simplify the first part actually, because we have 1 over 15 times 5, which we know would be 1 over 3, and then x to the power 4, so we could have x to the power 4 over 3 minus 2 times 1/2, which would actually be 1, and then we have in here x to the power 1 over 2. We know if it's negative, that means we have 1 over the value x of n, right? Sorry, there's no negative, it's 1 over xn. And now what is our n value? Well, that is 1 over 2. And so we should have 1 over the square root of 2, right? Because 1 over 2 is the same as square root. And so we get 1 over square root of x. Here, our answer is clear. As we know, 1 times anything just doesn't change it. And so our final answer is actually x to the power 4 divided by 3 minus 1 over the square root of x. Again, if you wanted to go through the derivation of this answer right here using the first principle, it would be really tedious. So that's why you should be really thankful for these rules. Now that we have a little bit of practice with deriving the derivative of those functions, we can actually apply it now to solve some problems. So I've actually gathered up 3 types of problems that you'll see in this chapter, and those are the following. The first one would be to determine the equation of a tangent. So you're going to be given a function, right? And then they're going to ask you like, hey, what is the equation of the tangent that touches x is equals to 1? And then you're going to be like, oh shoot, how do I do that? Well, here's the answer. To find the equation of the tangent, which we know is a straight line, we need the following information. We need y is equals to mx plus b, right? We know the x, y, and m values immediately off the bat because that's just the nature of the problem. The x value will be given in the question. The y value can also be given, I guess, but that would not necessarily give you one x point. So usually it will be just a single x value will be given, and then you'll be given an equation. So you could substitute x into that equation and immediately solve for y. So now you found the point that you're finding the tangent to. To find m, which is the slope, you'll actually need to find the first derivative of the function. Notice how, say, the first derivative That's because there's a lot of derivatives that you could do. Like if you take the derivative of a derivative, that's the second derivative. And so just to be super specific, we're talking about the first one here. So once you find the first derivative, you need to just substitute x into that equation. And now you've found m. Now you know y, x, and m, so all you have to do is solve for b, which you learned in grade 9. If you don't remember for some reason, all you gotta do is substitute the values in, and then you have one unknown, so it's really easy to solve for. The second type of problem that we have is actually related to instantaneous rate of change. So as you may recall, the derivative is simply just the graph of the rate of change of a function. So how does the graph x squared change? Oh well, its rate of change is actually having the graph of 2x, and that is what you need to understand for this chapter. So if you're asked to find the instantaneous rate of change for a function, then all that means is that you need to find the first derivative. If it's asking the instantaneous rate of change for x is equals to -7, then you would substitute -7 into your found equation of the first derivative, and that would give you the answer. Again, remember, the slope of the tangent, which is the value of the derivative at a certain point, is the exact same as its instantaneous rate of change. The last type of problem that you may face is to determine the tangent points for a given slope. So it's the exact opposite of question 1 over here. So again, just like with all the problems, you'll need to find the first derivative. Now, since you've been given the slope, as it says here, you were given the slope, you would substitute that into your equation, and then you could solve for x in this case. Once you find the values of x, that would mean that's where the tangent was present. And so you could use those same x values in the original equation and solve for y. Once you have your x and y values, you can easily just write x comma y, and you found the point that was like you had to find. So hopefully you understand how to solve these types of problems now. As some extra practice, here are 5 questions here. They're very, very simple. These ones are related to problem solving, and these ones are just simple derivative rule practice, so you can really practice how to derive and apply those derivative rules. Again, I'd like to say thank you to anybody who stayed this far in the video. You guys are truly awesome. If you have any questions or want to contact me for like math help, please leave a comment down below or like email me. Some of you have found my Instagram, which is also cool. But yeah, feel free to contact me any way you can, and I'll gladly help you out. But again, thank you so much, guys. Bye bye.